AutoVis, enabling collaborative mixed-immersive analysis of automotive user interface interaction studies. AutoVis is an analysis framework enabling the immersive and interactive analysis of in-vehicle interactions, passenger behavior, and physiology, combined with a replication of the vehicle environment and study context. The immersive virtual reality view combines 3D and 2D visualizations, enabling analysts to perceive data and the original spatial environment in real time. The desktop view enables the synchronized non-immersive overview of automotive UI studies. The 2D panel provides a holistic overview of 2D data as line diagrams and events. It hints at interesting sequences via outlier detection and horizontal lines showing the mean. The 3D scene panel replicates the original study environment using a virtual ego vehicle, other road users, passenger behavior, and environmental context. Besides, it hosts 2D visualizations, avatars, trajectories, and heatmaps. The timeline controls tool-wide playback of the 3D scene, video, and audio. Additionally, analysts can select and annotate sections on the timeline. AutoVis considers 4 event types. These events can show relevant sequences for further examination in virtual reality. The virtual reality view enables immersive analytics. Avatars replicate passenger movements from pre-recorded 3D skeleton data. An aggregated avatar visualizes the average positions and rotations of individual avatars. Trajectories visualize hand and head movements for a selected time frame. In-vehicle gaze and touch heatmaps provide an overview of interactions with interior surfaces. Environment gaze and pointing heatmaps accurately map the replicated 3D meshes of buildings and other road users. A traffic heatmap visualizes their positions. A tablet attached to the left controller displays study-related metrics, the 2D panel, and events. Analysts can quickly navigate through the scene via camera switches and the timeline. A minimap provides a top-down view of the analysis environment to improve analysts' navigation. AutoVis visualizes spatio-temporal events along the driving path, indicating the location and orientation of interaction, emotion, driving, and activity events. To visualize the link between in-vehicle interactions and environment, context portals provide a glimpse of the referenced context, for example a location or object, by showing a spatial portal next to an avatar's finger or head. Analysts can place annotations in space to leave hints, descriptions, and opinions about the analysis for collaborators or when switching between desktop and VR view. Besides, analysts can use the labels to annotate their dataset, for example, for supervised deep learning applications. The labels are automatically linked to the driving path events and the time frame within the dataset. In addition to desktop and VR, a pass-through VR view enables analysts to leverage a real vehicle's interior visuals, layout, and haptics for an immersive analysis specific to the automotive domain. AutoVis places the 3D visualizations at their intended positions within the real vehicle inferred from an analyst's dataset. They can selectively activate the pass-through for specific interior locations. Moreover, AutoVis enables collaborative analysis across time, space, and levels of immersion using desktop or VR view. We demonstrate AutoVis using authentic data from the use case of multimodal in-vehicle interaction. For this, we leverage a static driving simulator using the Vive Pro Eye with a built-in eye tracker, an Empatica E4 to record physiological signals, a Kinect for body tracking and a leap motion for hand tracking. A webcam captured visible behavior. We simulated a ride in an automated vehicle in downtown San Francisco. To represent a typical study, participants can freely interact with multiple modalities: touch, gesture, gaze, and speech. We employed 4 events relevant to multimodal UI research. First, participants had to query their current location in an in-vehicle navigation task while driving through Lombard Street. Then, another passenger entered the automated vehicle, transforming the vehicle into a social place. After that, the automated vehicle performed an unexpected emergency brake because a cyclist crossed the street. Finally, the participants referred to the Transamerica Pyramid and requested more information. We also provide a companion tool that pre-processes data according to the AutoVis data specification. The companion tool converts low-level signals such as pupil size into higher-level information such as cognitive load or drowsiness. We use state-of-the-art deep learning such as deep face, open pose, or YOLAV4. After loading viewing the data in AutoVis, analysts can start the analysis according to their research goals. In our use case, the goal is to investigate the usability of multimodal interactions depending on the context, time difference, order, and usage. The heat maps and the avatars help to identify behaviors. Some participants gazed directly at the target and pointed close to the gaze hit, while others pointed in the mirror directions with bent elbows. The action events on the timeline highlight a time difference between the interactions of 0.5 seconds. The head movements indicate that participants mostly ignored the other passenger, except during an initial conversation. The in-vehicle heatmaps show a widespread pattern, indicating that participants likely were curious about the unfamiliar setting and explored the interior by looking around and touching it. The heat maps in the environment also reveal that participants interacted with the unexpected cyclist. In our second use case, we demonstrate how AutoVis converts and visualizes real-world datasets. For this, we leverage Drive and Act, which is a dataset for driver activity recognition captured in manual and autonomous driving. In AutoVis, analysts can perceive the automatically recognized body positions and movements during driver activities from any point of view. In our third use case, we demonstrate how AutoVis integrates a real vehicle into an analysis process. For this, we recorded an exemplary dataset in a BMW 525i Touring to analyze a novel UI concept for an air conditioning control specific to the driver's seat. From the driver's point of view using pass-through VR, the analysts discover that participants primarily interacted with the center console instead of the driver door, where the novel UI was located. Besides, they found a mismatch between the door button layout of the real vehicle and the simulator vehicle used in the study. With AutoVis, analysts can re-experience the unique spatiality of automotive interactions with the interplay of in-vehicle and environmental contexts. The AutoVis approach aims to facilitate the analysis of human-vehicle interaction.